Okay, this video is about sp hybridization. So I'm going to start by talking about beryllium dihydride. Remember, beryllium violates the octet rule. It only has 2 valence electrons, and it only needs 4 for covalent bonding. It's a metal, so you don't usually think of metals as participating in covalent bonding, but it has such a relatively high electronegativity for metal that it will covalently bond. The electronegativity difference between beryllium and a lot of nonmetals is pretty small, so it forms covalent bonds. Let's start by looking at the atomic orbitals for beryllium, and I'll just focus on the outer energy level orbital. All he has is 2 electrons in that 2s orbital. He doesn't even, in the atomic orbitals, he doesn't even need to use his p orbitals as a kind of home base for his electrons in atomic orbitals. When beryllium hybridizes, the beryllium atom forms sp bonding orbitals. The other p orbitals that are not being used are just off here, not being used. So the 2 electrons that were originally in the 2s atomic orbital are now spread across the sp bonding orbitals. The hydrogens share an electron with the beryllium by contributing their single electron to each of these. And there is the complete sp bonding orbital model. sp orbitals stick straight out from each other 180 degrees. They are linear, whereas the s over here was a concentric sphere about the nucleus, and of course the p's were dumbbell shaped on the XYZ axes about the nucleus. The sp orbitals are similar to a p orbital, but just one single p orbital sticking straight out. So they stick out 180 degrees from each other. So that's the simplest form of sp hybridization. Now let's talk about a more complicated sp hybridization scheme, and I'll do that with respect to, where we go here, with respect to acetylene. Here's acetylene, C triple bond CH. Okay, so what we have with acetylene is let's see. We have a carbon that has a single bond to one hydrogen and a triple bond to the other carbon. So I'm just going to focus on the carbon here on the left to start with, and I'll make it my blue carbon. So this is going to be my blue carbon. Coming over here, in the atomic orbitals, he has 2s2, 2p2. When I make his sp hybridized orbitals over here, of course the sp orbitals are of equal energy, slightly higher than the 2s, slightly lower than the 2p, and he also has some p orbitals that are left over that are not involved in the hybridization process. That doesn't mean they're not involved in bonding. So if I come back over here to the hydrogen, I forgot to put my carbon electrons in my sp orbital. So here is 1 electron in the sp, another electron in an sp orbital, and following Hund's law, I just go straight across. I've got 2 electrons that are each going to get their own p orbital. So the 4 electrons that were in 2s and 2p over here on this side, are now over here spread out, and pretend like this is all equal energy. I know I kind of went up a little there. Okay, so I've got the 4 electrons spread across these bonding orbitals, and now the hydrogen over here on the far left is going to share his 1 electron with one of the sp hybrid orbitals, and I'm going to make this guy over here my red carbon, and so he is going to share an electron. And so what we have already is the single bond from between the carbon and the hydrogen, and the first part of the bond between the carbon and the other carbon. This would be a single bond. However, we have these p orbitals out here that each have one electron from the original blue carbon, and they are also going to share the orbitals with one electron from each of the red carbon. These two p orbitals will go into forming these multiple bonds. So what we saw in the last video for the C double bond, the ethylene, C double bond C with the 4 H's, was we had one leftover P that formed the double bond. Here we have two leftover P's. That's why we end up with a triple bond. So what we're going to learn is that single bonds, the original single bond here, would be considered a sigma bond. Okay, that's supposed to be a lowercase sigma. I think it looks more like a lowercase delta. Let me try to make a sigma. That is a lowercase Greek letter sigma. These guys over here represent what we call pi bonds. The pi bonds are the stuff that double and triple bonds are made of. So we have 1 sigma and 2 pi's. 1 sigma and 2 pi's is a triple bond.